I just wanted to thank you all for joining us for the CASA Moon Planetary Sample Science Seminar. People are slowly coming in. The seminar is sponsored by Survey, CASA Moon, the Institute of Meteoritics, and the UNM Grand Challenge. And we're really fortunate to have our today's speaker. He's calling in from Curtin University in Perth, where it is very early on Thursday morning. And so what I'd like to do is introduce Alexander Nemchin, and his talk will be on uranium-lead systematics of lunar samples. Sasha, go ahead.
Yeah, thanks, Chip. Okay, let's go straight into it. And considering big plans of our group to work with samples, I would like to kind of talk a little bit about what can be done with UPB chronology and UPB method. And we can, strictly speaking, split everything into three main groups we can deal with, of materials we can deal with, and one of them is, of course, uranium, represented by uranium-rich minerals, zircon, badellite, phosphates, and so on. And so on. Basalts is the second group, and finally glass beads. There was a bit of discussion over email about glass beads, and I was keeping quiet, just waiting for my talk. We can discuss a little bit more about some of these issues after my presentation. I will try not to go into big picture, what I would like to do, again, considering that we're planning to analyze quite a few samples, hopefully, in the future. Just give you some idea of what can be done, what potentially can represent some problems, and how we're trying to deal with them, sometimes successfully, sometimes not. But I pretty much want to go through our possible ways to work with the samples using UPB system, just following this kind of outline. And we'll start with uranium-rich minerals in a minute. But before we go, just a little bit of overview. So any sample we analyze with UPB probably can be viewed within three-stage model evolution of lead. And well, we start with, say, primordial lead here at time 0, time of formation of the moon, or lunar magma ocean, whichever way you like to call it. And we also got uranium-lead ratio, or 238:204. We will refer it to as mu, and our starting mu of, let's say, bulk silicate moon or lunar magma ocean, we are going to refer as mu 0 throughout the talk when we need it. And well, our lunar initial melt or magma ocean is evolving. Lead in this magma ocean is evolving along this red curve, pretty much. And then at some point we form a source by crystallizing parts of this magma ocean, source of our rock we eventually are going to study. And well, we can refer to time of formation of this source as T1, and again, uranium-lead ratio we will refer to as mu1. And finally, at the end of this second stage, we get the rock we're going to study at time t. So this is the age of our rock, and our lead reaches this point here. Our isotopic composition of lead reaches this point here, and this is our initial lead of material we are studying. From that point, we're starting lead evolution within our sample. And depending on uranium-lead ratio in different parts of the sample is going to vary, we will pretty much get our lead along the green line here. So whatever we're measuring today is somehow going to be distributed along this green line. Anything without initial lead is going to be here in this lower corner, and that would represent our age. We can calculate the age out of this value. It also intercepts of this green line with vertical axis. So in many cases, we're looking for this intercept. If some of our materials within our sample or some minerals, phases, and so on have a little bit of contribution of initial lead, they will be pulled up along the green line. And of course, there is the contamination. Whatever we do, no matter how careful we are in sample preparation, no matter how careful we are with cleaning of the samples, we still cannot completely eliminate possibility of terrestrial contamination. Okay, so our different materials will be sitting within this triangle more or less, depending on amount of contamination. If there is no contamination or very little contamination, they will probably be sitting along this green line. Say our zirconium-rich phases, and then are going to be very close to this corner, defining age. They are best to define the age. Some phosphates may have a little bit of initial, so they will be drifting up a little bit. Different phases in basals will be spread all over the place, and glasses potentially can be distributed along this green line, and then different glasses will you'll find them in different parts or different places along this green line. Okay, so let's go and then start thinking about or looking at what can be done with different materials, starting with uranium-rich minerals. Initially, when we started it many years ago, well, about 15 years ago, we focused on large zircon grains found in breccias, where they are individual fragments disconnected from their source rocks. And then you can go so far with this type of materials because you lost petrogenetic context. More recently, we started concentrating on the smaller grains that we find within the rocks. And I will show a few examples of that. And the first one, we finding quite a few of impact melt fragments in Apollo 14 soils. One of them was identified by Brett Jolliffe long time ago, and we made a few attempts to date them, and these fragments are quite creepy. Well, you can see that zirconium content is quite high and thorium content is very high, and they're full of both phosphates and zircons. And well, okay, this slide pretty much illustrates a range of different things we can see, a range of different zircons and phosphates we can see in the samples. And then first of all, there are some grains that look like fragments, broken fragments. They're larger than surrounding matrix, and this is example of apatite, and then this one represent example of zircon. So they look like they inherited by this impact. They coming from the target. On the other hand, well, there are phosphates like the apatite and perlite here, and then zircons that clearly growing from the melt. They pretty much part of this assemblage of pyroxenes and plagioclase. And then they've got sometimes intricate terminations. It's very hard to imagine that they are fragments surviving impact event. In addition to that, when we look carefully, zircons, some of the zircons show these granular features, And over the years, we learned that these granular zircons actually formed during the impact as a result of the impact. So here we've got something that is inherited, and both phosphates and zircons that are formed as a result of impact. And so when we start looking at ages, well, if we dump everything together, it looks like a mess. And that's why Brett started looking at the samples probably 10 years ago. And initially, when they saw that, they didn't really know what to do with that. 10 years later, we learned quite a lot about zircons, so we can provide sensible interpretation, we think. Okay, so the different colors show different types of things. So light blue is what we believe or interpret as zircon class. Red is zircon that formed clearly formed in a melt and in plus granular zircons. Blue, it's kind of doubtful. We don't really know. It may be both. And then very light green is phosphates. Okay, and if you look at the first diagram, there is a spread sort of between 4.3 and 3.9. And majority of the zircons are kind of focusing here, probably, and most of phosphates are at the lower part of this diagram. And it makes sense. Zircon is more stable. It's more difficult to reset. Phosphates are much easier to reset. So the interpretation we're trying to push forward is that, well, okay, this whole assemblage, except, well, okay, zircon class that are inherited from the target are formed. Well, the other zircons that are formed in the melt, they probably formed around 4.3. And phosphates, most of phosphates are formed at the same time. But then there was a second event at around 3.9, and then, well, zircons were reset partly, but not as much as phosphates. So we can see these two events. And, well, okay, if we clear some of these intermediately partially reset materials, we'll find that zircons sitting at the very top and then representing single population, well, okay, class are slightly older, but not really indistinguishable, distinguishable from the group of zircons we believe formed in the melt in terms of age. Well, the stuff that is formed in the melt is 4.324 million years, and then we think that is the age of formation of the melt. We don't really know where the target was formed just before this event, or these inherited pieces were reset by impact. But anyway, these pieces of melt experienced the second event at 3.9 that reset appetites quite substantially, and the age is 3922, which we believe is Imbrium impact. So the idea here is that, well, yes, okay, somehow we formed the impact melt at 4.325 or something like that. Pieces of this material were caught in Imbrium ejecta. Well, we don't know whether they're coming from the target, from the basin itself, or they've been sitting at Apollo 14 landing site waiting for the ejector to come in, and were incorporated into it and then reheated and reset. But this is the story we can come up from the study of these pieces. Okay, so another example, and again, what we're trying to do is to use multiple minerals. If zircon and phosphates are present, it's great. If bedelite and phosphates are present, again, it's very good because they've got these different resetting temperatures And then so we can see if some complexity exists in the sample. And then say we've got the second example, NWA 5000, I don't know, about 10 years ago. For some reason, everybody was fast about it. And I was specifically avoiding working with this sample. But more recently, one of my postdocs started looking at that. And what we found that, well, it has phosphates and bdelliite. And when we date them, they pretty much give us indistinguishable ages. So whatever the interpretation of the sample is, it has very simple history. Both bdelliite and phosphates give us the same age. And well, okay, again, as I mentioned before, I'm not going to go into big picture and try to interpret every single sample I show. Here, I'm trying to demonstrate what is possible, what is not possible, and then point out some complexities. Okay, the last example. Again, most of things I'm showing are not published. Some new stuff. Okay, so another last example from this group of materials is represented by lunar 16 granulite fragments. And again, granulites, I've never really looked at them before recently. But again, all of a sudden we found that some of these materials contain quite a lot of phosphates. And then, well, yellow bits here are all phosphates, and some zirconium-rich minerals. Okay, so some enlarged pieces. This is phosphate, this is zircon, and they look like they form texturally form within this material together with the rest. So they're not pieces incorporated. They're not older. They are part of this rock. So if we manage to date them, then we're gonna get the age of the rock. Again, whatever it means for the big picture, we can talk about it at some point later in this story for another day. And well, okay, if we've got materials that, I don't know, say larger than 5 microns, then we got a reasonably good chance to get ages. Okay, so okay, when we start looking at this these pieces in this particular case, it's a little bit more complicated. So if we look at diagram at the top left, 7,6 lead, 4,6 lead, it's just lead diagram, similar to what I showed at the start. You can see this is the corner where we've got probably most radiogenic lead with no initial, but a lot of our analysis are going up. So they contain a little bit of initial lead, or maybe they contain a little bit of contamination. We don't necessarily know straight away. Okay, intercept of this line fitted through this analysis would give us an age of about 470 plus and minus 17. Okay, analyzing zircons and phosphates, we've got uranium, of course, so we can utilize uranium lead systematics to get more information from our analysis. But before we go that, sort of looking at this diagram, we can probably end, okay, well, it's expanded to show terrestrial lead composition. So our line is almost invisible because it's very close to vertical axis, which means that we're not getting a lot of contamination here. So our pull of these points up is probably a representation of initial lunar composition. And then so we can try to constrain line in 3D utilizing uranium lead systematics. So, the idea here is that, well, okay, this is at the bottom, darker gray is our Concordia plane. And our measured lead for each of our points is hanging somewhere. This left side, lighter gray, is what is called common lead part. So it's 4676, pretty much this bit here. And again, in 3D, our analysis is hanging in space. And if the systematics is simple, then the series of analysis would form a line. And then this line will intercept Concordia plane, right where Concordia curve is, corresponding to the edge. And the other end of the line will intercept our common lead plane where initial composition is. And so we can constrain this line and, well, okay, this is line constraint. So the colors here are a bit tricky. Phosphates are green, zircons are red, and blue, dark blue, is projection of all this analysis along the line. And you can see they are projected tightly, reasonably tightly to the Concordia, and we can estimate the age, which is 479, which is not different from our intercept age. And we also can estimate intercepts of our common lead plane, which is highly radiogenic. Again, it's indication that it's lunar. So we're probably tapping into initial composition here. So the composition that the rock had when it formed. Okay, so this pretty much completes or illustrates semi what I wanted to talk about, discussing uranium-rich minerals. And we find phosphates certainly in a lot of different lunar rocks, so we can utilize the systematics. In many of them, we also find small zirconium-rich phases that we can use. So it's not necessarily restricted to examples I showed. And we can work with small fragments. So quite a lot of these pieces are actually small fragments extracted from soils. Okay, let's switch and talk about basals. We published quite a lot about basals in the last, whatever, 5-10 years. So I'm going to show you a couple of most recent examples. And again, lunar 16 fragments. There are two types recognized in the soil from lunar 16. One is more or less kind of major components, main group, low to intermediate titanium basals, and there are small fragments, so small pieces of small proportion of VLT basals there as well. Now the lower part shows kind of metastasis. That's what we're trying to target, because plagioclase and pyroxene do not contain really a lot of uranium and not a lot of lead. We tried a few times to analyze them, but the counts are so low we can hardly see it. We can conclude that major components in these rocks do not contain reasonable amounts of lead we can deal with. So we're focusing on pockets of metastasis, and they're messy, of course. And the idea here is that we cannot really validate. There are some phosphates, there are some potassium feldspars there. Sometimes there are some baddellites. Sometimes you can even find zircons, but they are so small. I said 5 microns. That's probably what we can handle when we're talking about uranium-rich minerals. In basals, they're very small. We cannot put a SIM spot into single phase without hitting 20 others that surround it. So the approach here is different. We're not analyzing uranium anymore because we cannot focus our spot into single phase. We know that we're analyzing mixtures, but we're randomly analyzing these mixtures in a hope that some of them would contain a little bit more of uranium-rich minerals, and would be closer to our intercept. Some of them will contain less, and will be further away. So, okay, well, I mentioned that we've got VLT and kind of normal intermediate type of bustles there. But important thing is that, as I said, we randomly analyze a lot of different spots, and then some of them contain more of uranium-rich minerals, some of them contain less, and then so as a result, you hope to get what is called isochron. Yes, well, okay, sometimes you've got contamination, and contamination would move the analysis to the right. Our terrestrial composition is outside of this graph, outside of this plot, to the right. But nevertheless, what we then do, we analyze a lot of points, and we filter everything that falls to the right. We're trying to identify this leftmost best fit line, and believe that it represents lunar lead mixture of this very radiogenic material and initial composition type of lead, free of contamination. And then so when we identify this line, we believe that we got the age from the intercept of the line. Again, we cannot analyze uranium here because we're targeting very small, or phases in our targets are very small. So we're analyzing multiple phases in a single spot. So when we look at, again, in this particular example, lunar 16 bustles, main group appears to have an age of 3590 plus or minus 9, and VLT much older, 3919. But again, I'm not going to go into detail and discuss what it all means. It's just an illustration of possibilities. Now, just a little bit of kind of overview of what we achieved in the last, 10 years. We started it, I think about 13, 15 or something like that. So I tried to put it all together in terms of ages and using classification provided by Clive long time ago. And then starting from VLT, okay, then low aluminium, high aluminium, it's rotated compared to Clive's paper because I needed to show the ages. So, and we don't have a lot of VLT bustles except the one I showed a minute ago from lunar 16, but some of these meteorites are probably fall into VLT groups. And well, it looks like we're getting reasonably consistent ages when we're analyzing similar materials. If we go further to low titanium, it's much more populated because, of course, we've got access to quite a lot of Apollo 12, Apollo 15 samples, and then probably some meteorites. Important thing to point out here is that, say, if you look at Apollo 15, olivine-rich materials are quite close together and much younger than quartz. Normative bustles, and it looks like both groups are formed within the eras pretty much. And then, if you go back to Apollo 12, same applies to ilmenite bustles at Apollo 12. But it doesn't look like pigeonite and olivine bustles actually form a tight age group. There is about 50 million years difference between two samples we analyze here, and then probably around 40 or 50 million years between different samples in olivine bustles. So whatever it means, I don't necessarily know. Again, it's probably topic for discussion for another day. But there are some groups we analyzed within the set that show very tight spread. They pretty much all samples are within the error, and there are some where it's kind of goes beyond the error. So probably you're having multiple pulses or multiple flows that form through a certain period of time. And same applies for, when we start looking at high titanium basals. Interesting thing that pretty much everything at Apollo 17 side is of the same age. And if we go to Apollo 11, then you've got almost 300 million years difference between different groups of basals. Within the individual groups, they quite nicely, well, they're quite similar. But overall, there is, yes, if you start from 1003, which is 3854, and then sort of go to type A, Apollo 11 basals, they are 3580, 3550 or something like that. So we here in Apollo 11, we've got much more extended period of basal formation for whatever reason. Okay, and I said that yeah, I'm not going to go into detail. Let me check my timing. Yes, pretty much. We've got a bit of time to go into. I was considering skipping this part, but let's think a little bit about it. Considering that Lars is there, I would like him to see it because we need to talk about it at some point. So from basals, from analysis of basals, we're not only getting ages, but also initial compositions. And remember that this diagram I started, there is 3 stages. We've got these 3 stages, T0 somewhere to the right, and now we've got age of formation of basal source, and then different basaltic sources can form. Important thing is that if we started from the same point here, then everything with the same time or formed at the same time from different basaltic sources would be, we would expect every single sample falling on the line. So the older material is here, the younger you get, you shifting further down towards the horizontal axis. And that's what we see in a way. All these Apollo 17 and all the Apollo 11 basals are kind of concentrated here. 8 type A Apollo 11 basals are here. They're younger, so they lower with respect to 7, 6. And they also shifted to the right. These curves are quite steep, so we cannot explain this difference by evolution of the same source. There is a difference in mu value. We're looking at one curve probably going like that, and the second curve going like that. There is also the age difference. So this material sits somewhere here. Group A, Apollo 11 samples, sit somewhere here. That this is how we can explain within the framework of this evolution curves. But we can push it a little bit further, having what about 10 or so samples. We can try to investigate what is happening with evolution before the formation of the source or before the formation of basals. Again, bringing these equations, you don't necessarily need to worry about it. We're looking at 3 stages, but we can rearrange these equations. And within that system of 2 equations, we know initial composition of our basals, of all our basals, and their ages. What we don't know time of formation of the moon or lunar magma ocean. We don't know time of formation of sources of these basals. We don't know mu of lunar magma ocean, and we don't know mu of the sources of our source. Nevertheless, we've got two equations for unknowns, but we can play a little bit and at least try to establish some limits for these parameters. Okay, so, well, we assume also that primordial composition is that of canyon diablo-troilite. Yes, there is a bit of history before the moon was formed, but it happens at very low mu value. So we kind of, at this stage, we think it's probably not introducing a lot of difference, uncertainty, and accuracy. Okay, so time of the moon formation is also time of LMO formation. And we also believe or assume that mu0, mu of the LMO, is all the same. It's not changing through the crystallization of LMO as a result of crystallization, simply because uranium and lead are strongly incompatible, so they will stick to the melt. And then, well, okay, source solids will change mu, but the melt, coexisting melt, will not. This is the idea. And then, well, okay, with modern computing technology, we can pretty much say, okay, well, let's put the limits and then say T0 is probably not going to go older than formation of solar system. And it's probably not going to be younger than what neodymium, hafnium, and also lead systematics tells us about whatever crystallization of lunar magma ocean 350, for example. Well, we can also set some limits for mu0, say between 0 and 6,000. We can go 10, doesn't really matter, because we're trying to estimate limits of these all parameters. And as you will see in a minute, they pretty much will be independent on selection, of precise selection of these ranges. Okay, so we with modern computing power, we can pretty much go from 4570 and then 4350 with a step of 1 million years, and then we can do the same from 0 to 6,000 and estimate T1 and mu1 using our two equations for each step. So we can do millions of steps and get T1 and mu1. Okay, so some of the solutions are going to be completely crazy. So we usually filter this solution. So we don't want T1 be larger than T0. We don't want our source formed before the moon formed. We also don't want mu1 to be more than mu0, again, because of partitioning. And, well, okay, let's limit T1 to 4.3 million years. And, well, okay, when we do that, then first observation we can make is that all mu's for all our sources have surprisingly very narrow range, irrespective of what we put for, or what we use for time of formation of the moon or mu of lunar magma ocean. So we can get mu of the sources for our basaltic rocks from this modeling, well, with a reasonable kind of degree of uncertainty. The second observation, and I was kind of avoiding talking about age of the moon, but, well, okay, we may as well start doing it. Second observation coming from here is that there are no solutions that satisfy our conditions that are viable if the age of the moon is older than 4420. So remember, we've been trying everything from 4.570, but most of all these solutions above this dashed line were rejected because they did not make sense. I don't know, Lars probably is going to be happy about it. Similarly, there are no solutions. Remember, we've been running mu0 from 0 to 6,000, but there are no satisfactory solutions if mu is smaller than 1,300, which is kind of interesting. Again, maybe we can discuss what it means in terms of overall lunar evolution. And then, well, okay, it doesn't really matter. I just put it here. The significance of that, I still don't quite understand. But it looks like if we plot mu of the source versus h, there is initial decrease in mu value, and then, well, towards type A, Apollo 11 Basels, it jumps up again. Okay, I'll leave that. That I promise that I'm not going to go into complex things. So let's go back to simpler things. Okay, glasses, last bit I would like to discuss. And we start with Picriti glasses, Apollo 17. We did a bit of work on these glasses, and well, okay, yes, there are different textual things, and Mark Norman, as far as I remember, identified homogeneous and 3 types of textured picritic glasses: microcrystalline, acicular, and porphyritic vitrifiers. And well, we when we started working with glasses, we tried to do I don't know, mostly homogeneous glasses, which probably was correct. With this project, we decided, okay, let's see if we can get sensible data from something where we've got crystals. And well, okay, the overall population consists of standard kind of set up. We've got quite a lot of picritic glasses in the sample, and then highlights and Murray. But we're not going to really talk about it at this point, a bit later in the talk. And so, well, okay, different textures, we try to plot it and analyze them separately. They form, again, when we look at letter system 7.6 versus 4.6, they seems to be following in the line, which kind of goes somewhere between terrestrial and meteoritic. There are a few points that, or few analyses that seems to be dragged towards initial composition, but majority of them probably are representing terrestrial contamination to some extent. I said that we probably was a good idea to stick with homogeneous glasses, because what we see looks like that there is some sort of lead loss in all textured materials. The homogeneous glasses giving us the age 36, 67, well, 68 plus and minus 9. Everything where we've got crystals seems to be drifting downwards to a different degree. Again, we can play the same game because we've got uranium analyzed here, so we don't necessarily want to rely only on 7.6. We can play the same game, 3-dimensional constraints from uranium-lead systematics. We use homogeneous glasses only here, and we try to constrain the line. Red ellipses are uncorrected data. Green ellipses are projected along the line, so we can get the age, which is similar to 7.6 intercept pretty much, 36, 65 plus and minus 11. But we also can get common lead intercept, and it looks like within the errors, it's pretty much terrestrial length. Okay, well, and we started analyzing these things because we can. Now I'm reasonably confident that if you give us, I don't know, a set of picritic glasses characterized, we can give you age with reasonable time frame. So we looked at Apollo 11 glasses, and chemically, it appears that our sample at least contains, well, normal high titanium, what you expect at Apollo 11, and a few low titanium and few VLT glasses. We still didn't get to the completion of analytical work. So low titanium glasses I cannot really talk about. We analyzed quite a lot of high titanium, and again, the same approach. 3D line constraint, H is 3655. Very similar to actually Apollo 17 glasses we analyzed. Again, same deal. Intercept of Concordia or intercept of common lead plane is most likely terrestrial contamination. We analyzed a few VLT glasses, and they are much younger, 3305. And because we've got only a few, so the precision is a bit worse. As I said, we are in the process of finishing this work right now. So it will be done this week. Okay, last bit. Impact glasses, more complicated, as you can see. So again, 7.6 diagram, terrestrial meteoritical lead, and the mass of, and I'm only taking Murray glasses here, Highlands glasses, Highlands Murray, using Ryan's paper and classification, just to illustrate the point. When we're dealing with impact glasses, it's more complicated. You can see that quite a lot of them pretty much full of terrestrial lead, or maybe, we don't know, maybe some of them are actually containing meteoritic lead. Well, there is a lot here, which is good. They're close to the real age, so to speak. There are some full of lunar lead, and when we look at Concordia, and these three Concordia plots are pretty much expanding the same plot. So this is the full data set. Then it's zoomed in closer to vertical axis and zoomed in again. So you can see quite a lot of them are concordant. And again, these guys are reasonably easy to work with because they require very little correction. But there is still quite a large group over here which present serious problems. Because when we start thinking about what lead we can have in some of these glasses, we try to visualize it with Mark Norman a few times, and we come up with this following list of possibilities. Yes, okay, well, first of all, we probably have lead formed by in situ decay within the glasses, and they represent age. So it would be sitting somewhere on the vertical axis and somewhere on the Concordia, on Concordia diagram. Then we probably most likely have terrestrial contamination of various degree. So this is the lead, and on Concordia diagrams, it is going to be here where the green dot is. Well, there is a possibility of meteoritic lead in impact glasses because, yeah, okay, if you imagine surface, it accumulates all the stuff that comes from space, and then you've got impact that produces glass bits, and it can potentially incorporate this meteoritic material accumulated on the surface into the glass bits. So we cannot completely exclude it. Okay, so then there is initial lead, like in every sample. There is a possibility that not all initial lead was degassed during formation of the glass, even though when we started this work, again, a few years back, our expectation was it is going to be easy because most of this initial lead would be outgassed out of the bit. Not the case. we now recognize that a lot of it can survive. And then what we call unsupported lead, the idea is that there is lead. We know from the early work on lead isotopes in soils that there is lead that was separated at some point from uranium and exists within the soil, and it can be it can diffuse into glasses if there is a close contact, and so it's going to be slightly different in composition. And I try to kind of visualize where they are. Unsupported lead is going to be quite radiogenic, formed early, and let me see what, and going to be somewhere here where this red blob is. An initial lead, because it's not separate from uranium. Say you've got basaltic flow, and you're accumulating lead through the life of through existence of these basalts on the surface after it's formed. And this lead will be evolving along this blue, light blue curve. And then if you form glass beads by impacting this basaltic unit, then you potentially can incorporate lead, depending on the time, of course, of this impact, anyway along this blue curve. And the same on the Concordia diagram. So the composition of initial lead is going to be quite white, depending on the age, of course. Older materials are going to be here, younger materials, younger glasses are going to be here in terms of initial composition. So when we're correcting, it creates a problem because say, okay, well, we've got one ellipse that we want to correct, and it's quite far from Concordia. So if we say we believe that it's unsupported lead that shifts it here, then we will be correcting along this line here and finish with the age of about 30 million years. But if we believe that it's not unsupported by initial composition, then we'll be correcting along or projecting it along this line, and it will intercept Concordia curve somewhere to the right, and the age would be very young, whatever, 5 million years or whatever. So it's much easier or less, well, the points that are close to Concordia are less sensitive, of course, to that. So there is not a lot of difference when we're correcting this type of analysis. If you project it from here or from here, then the problem starts again when you start getting point along the vertical part of or semi-vertical part of the curve, because again you're projecting it almost parallel to the curve, so there is a wide range of possibilities here, and it becomes complicated. So it's tricky. You need to somehow deal with this multiple sources. We try to find a way, again, three-dimensional correction. We added uranium-thorium systematics, and in this case, you can kind of take into account this type of lead and only deal with remaining two-component unsupported and initial, and you can calculate the age for each individual bit, and then you run into the next problem. Okay, you've got a whole bunch of individual ages for individual glasses, and then how you present this data. And we try different ways, and I'm kind of trying to show you. This is histogram of distribution for apollo glasses, and this is standard PDF or probability density function. You can see PDF identifies a lot of peaks here, but if I try to do Gaussian unmixing, for example, it only recognizes 5 major peaks. So there is a difference, and we don't really know what is the best, the best way of deal with this large arrays of data. And then, well, I guess if we're gonna go there, we probably need to collectively discuss it. And well, it's probably not going to be ideal solution, but at least we need to work in exactly the same way, so we can compare different sets of data. Okay, just to finish, one single point on the problem of correcting for initial lead. We started to think about approach that it's more time consuming, but nevertheless, maybe it will work. And it kind of, we found it by accident. There was this one single chunky glass piece that looked like potentially picritic in composition, and well, texturally, there is some recrystallization here. And then so we wanted to really analyze and get it the age, so we put multiple spots into it. And then so when we put multiple spots into it, then you can start applying the approach we used for volcanic glasses. You can try to constrain line through multiple spots in 3D, and here is the result of that. Of course, it's probably not picritic, its impact, because of the age, but we analyze whatever 5 or 6 spots here. We project the line again. Red ellipses are uncorrected data. Green ellipses are projected along the line. The age is 68 plus or minus 10. And well, okay, within the errors, common lead appears to be terrestrial. And I will stop on that. I'm pretty sure you've got quite a bit to digest. Thank you.
Thank you very much, Sasha.
Yeah.
Do we have questions from the audience?
I have a lot to think about here. That was a tour de force, Sasha, and really great. You know, it's interesting the conclusions you come up with regarding the evolution of lead, because they're very analogous to the conclusions that we came up with looking at the rubidium-strontium system, which is similar in the sense that it has a volatile parent-daughter and a refractory parent-daughter. And the thing that I just wanted to note was that your initial mu value is much higher than your mu1. So your mu0 is, I think, was 1300 or above, and your mu1 was like 500 or 600. And so if you think about that in a broad sense, it implies that there's an actual enrichment in volatile elements somewhere, you know, in the pathway. And what we concluded from RBSR was actually the mixing of the Earth in with the moon during the giant impact. So I don't know if that scenario would fit for what you're looking at, but it seems to be fairly analogous.
Yeah, we're tossing different possibilities at the moment with Jim, and then probably at some stage would be good to discuss it with you. Yeah, some way it's very difficult to get this different mu values simply by fractional crystallization. That's for sure. So we will playing with the idea that maybe we're losing volatiles somewhere in the process towards the end of LMO crystallization. But again, yeah, I need to think about what you said. It's possible that we're looking at the same kind of stuff.
Well, what we did with the rubidium-strontium was we found that, you know, something like Thea and before has a composition that doesn't look too different from angrite, say. So really volatile element depleted. And then what happens is you have a giant impact with a volatile depleted, but more volatile enriched moon, and Earth, or proto-Earth. And then you add a little bit of that in there to you know get your volatile elements up to what we see for the moon today, and that seemed to be the best fit to the modeling we did, and it seemed analogous to your shift from 1300 to 600 in mu values.
Yeah, yeah. I think well, we discussed this possibility, but decided to leave it until we can exhaust all other internal sort of to the moon options, and then yeah, it certainly could be the case.
Yeah,
Okay, I'm going to open this up to other questions, if that's okay, guys.
yeah,
Yeah, sure.
just finish that 1 point, Chip, and then I'll bug out.
Okay.
Consider the stable volatile elements in your volatile element modeling too, like zinc and gallium and
Yeah.
stuff, because there's a lot of constraints there too. Okay, thanks.
Great. Thanks, Lars. Any other questions from online? Any questions in the audience at UNM? Sasha, I did have a question. I was really kind of looking hard at your diagrams that you were identifying the sources, the lead characteristic of the sources for the Mare basalts, but then also looking at how those sources compare with the volcanic glasses. And I just didn't get there yet. Are there differences between, let's say, the Apollo 17 glass beads and the associated high titanium crystalline Mare basalts from the Apollo 17 area?
In terms of sources, it's at this stage it's difficult to say because most of our glasses do not give us indication of initial composition.
Okay.
They are
Okay.
pretty much mixtures between contamination and then purely in situ lead.
Okay.
So it's difficult to tell. In terms of ages, well, okay, there is at least with the set we analyzed, there is about 50 million years difference between Mare basalts and glasses. Glasses are younger.
Oh, okay. Okay. Great. And the analyses you did on the glasses to get those ages, were they from any particular location within the drive tube or in various locations within the drive tube?
We at the moment we are not dealing with drive tubes. At some point, long time ago, I asked for just Apollo 17 soil. I don't necessarily remember 7503 or something like that.
Okay.
And we just extracted it's surface material, so we extracted that from the surface.
Okay.
We
Any other
can,
questions? Go ahead, Sash.
yeah,
Sasha.
we can discuss drive tube now
Okay.
or later.
Okay. Great. Any other questions from people online? No, I think that's it. Well, I think you, Lars, and I have plenty to discuss over the next year through CASA Moon, and I really look forward to it. And thank you so much for taking your very early morning and joining us today.
Yeah, it's great. Thank you.
And then I also want to let everybody online know that next week's speaker is James Doughton from Brown University, and he'll be speaking upon, his talk is focusing upon lunar materials and the behavior of sulfur isotopes on the moon. Again, this talk, as all the others, are being recorded, and they will be online at the survey website that is also accessible through the CASA Moon website. I want to thank you all for joining us. And again, Sasha, thank you so much for giving us this presentation.
Yeah, my pleasure. Thank you.